Hey guys, this is my video on the integral, which is another operator in calculus. So the calculus operators are the derivative and the integral. So I have this function f of x here, an arbitrary function, and I want to find the area under this curve between x equals a and x equals b. So I can approximate this area by using a Riemann sum. So what I'm going to do is I'm going to start building some rectangles. And the rectangles are going to touch the curve of f of x right at the edge that starts the rectangle. Make these rectangles kind of big. They should all be about the same length. Or not the same length, but the same width. And as I do this, what we're going to end up doing is we're going to add up the areas of all of these rectangles to approximate the area under the curve between A and B. So we can do our final rectangle right here. So you can see this is an okay approximation. It's not amazing, but it's all right. And we can just call this, where this rectangle starts, is x1. The rectangle starts at x2, and all of these x values should be evenly spaced. It's going to be x3, be x4, and these are just subscripts on it, x5, x6, and x7. These are the starting points for the rectangles. I didn't do this because no rectangle starts here. Okay, so now we can sum up the areas of each rectangle. So the width of each rectangle, as I said, they're evenly spaced, and that's actually going to be, the width of each rectangle is going to be b minus a, so the width is going to be b minus a, that's this length here, divided by big N, the number of subdivisions we have. So we have 7 here, 7 rectangles, and since each of them are evenly spaced, each of them are 1/7 of this length, their width. The height of each rectangle will vary, and it's going to be the function f evaluated at x, we can call it x sub j, where j can be anything from 1 to n, which is 7 in this case. And now we can add this all up. So this is going to be f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5 plus f of x6 plus f of x7, and all of that times b minus a over 7. That's a long expression to write, so we can condense it to sigma notation. It's the capital sigma. It is a Greek letter. And so this just means we're summing all the terms, and we are going to sum each area. So each area is f of x sub j. Remember, this is a rectangle, so it's just width times height. So the width is b minus a over n. The height is f of x sub j. So it's height times width times b minus a divided by big N. And so we are going to sum from j is equal to 1 all the way to j is equal to n. This is our general formula for the Riemann sum approximation. And again, just like the derivative, is we can use limits to get a more exact answer. So you can see how if we have an infinite number of these rectangles, right, which would make the width of the rectangle go down, we could really accurately, we'll get rectangles really small, really small. You can see how that would very accurately find the area under the curve. And the limit is n approaches infinity, which would also be the limit as the width approaches 0, will give us the correct area. Also, just to note that these, when it's under the x-axis, when the function is negative, it is considered negative area, and that's very useful and very important. So that would give us, f of x3 is negative. That would make this this area be considered negative. F of x4 is negative. That would make this area be negative. So that's just the convention we use, and it is very, very important to have that. So we can now define the integral, right? Integral is going to be this little s thing. The integral from a to b of the function f of x. We're going to use this d again, this differential dx, and we need this for an integral because the integral is basically an infinite sum of all the rectangles, and dx represents the infinitesimal, the infinitely small width, and this represents, of course, the height. And that is equal to, we can define it as the limit as big N approaches infinity of the sum. So the integral is really just an infinite sum. It's the limit of a sum, and that's going to be important to understand. So from j equals 1 to n, f of x sub j times b minus a over n. And realize that this sum, if we switched a and b here, this term would be switched, right? If this was from b to a, the lower bound was b and the upper bound was a, this term would be flipped. And if it's the same situation, in fact, we can have an identity here. First, I'll box this in. This is our definition of the integral. The integral from a to b, f of x dx, is equal to negative the integral, same integral, but from b to a. But the argument of the integral is going to be the same. It's f of x dx. And see through this formula why that is true. But there's got to be a better way to do this. This limit has got to be really, really hard to evaluate, and thankfully there is an easier way to do it. So I'm going to, hopefully you've got these definitions down. You don't, pause the video and get them down, and I'll erase this stuff so we can go on to take the rules of taking integrals. Now, I'm not going into the integral's connection to the derivative, but I will tell you that there is one, and I will have some links in the description to that. It's called the fundamental theorem of calculus, and I'm not really going to go into that, but that said, I'll touch on it in this video. I'll mention it, but it's really going to be links in the description that will tell you more about it. Okay, so we are evaluating the integral from a to b of some function f of x dx. Now, this is called the definite integral because it has definite bounds. But this is equal to, there's actually going to be an integral function. It's going to be, I'm going to call that capital F of x. Now, this is really a lowercase f. That lowercase didn't really help, but it's a lowercase f. It's capital F of x. And we're going to have this line here. That means we're evaluating it at a and b. And this just means that is capital F of b minus capital F of a. So this is how we evaluate a definite integral, and then we just have to find this function f. And we are not going to really be doing that much in this course. If we ever need to have this, I'll have a table up or just a definition up of what the integral function is. But it is useful to know that this integral function, capital F of x, is equal to, we're going to have the same integral symbol, but we're not going to have any bounds on it. This is f of x, lowercase f of x. Fix that. Lowercase f of x dx. And this is called the indefinite integral. So this is our definite integral. This is our indefinite integral. And we just define this indefinite integral function. Then we evaluate it at a and b. And I may use the symbol a little bit with the line, and then evaluated at a and b. That is just evaluated at b minus evaluated at a. Okay, so we're not going to go into this. However, I can just tell you the fundamental theorem of calculus states that, in fact, capital F prime of x is equal to lowercase f of x. Which means that this indefinite integral function is actually the antiderivative of f, but you can look more into that with the links in the description. I just want to go through one more rule with integrals, and I can do it over here. And that is, there is one rule that we are going to need to use a lot in this course, and it is the sum rule for integrals. So I'm going to do this just with indefinite integrals, but note that this also works with definite integrals. I just keep it general, but you can imagine stuff on the boundary terms. So the indefinite integral of a plus b dx is equal to the integral a dx, running out of room, plus integral b dx. So really this integral thing does distribute just like a derivative does. So the integral of a sum is equal to the sum of the integrals. And you can, of course, also generalize this to more than two terms. So that is the integral. We have, on the previous slide, we had the definition of the integral in terms of limit, and now we have the definition of a definite integral in terms of a indefinite integral. And both of these, both the definite and the indefinite integral, will appear in quantum mechanics. It will really be, the indefinite integral will appear because we are trying to evaluate the definite integral. And if this doesn't make sense to you, I do have some more links in the description to videos that go more in depth onto the integral.